Good morning, everybody. All right. So hopefully everybody can hear me. So before I forget, let's everybody go ahead and please log into your Clicker accounts. We'll be doing a few of those problems today. So one of the things that I wanted to mention this morning was I sent out an email with a link for those people that need to excuse themselves from attendance every once in a while. So I want to show you just what that looks like in case you haven't taken a look. So let me just get that going here. Yeah, so let me go ahead and so before we continue with today's lecture, I just want to show everybody what that looks like. And yeah, so let's do that real quick. All right. So in the emails that I just sent, that hopefully you guys should have gotten, you should have something that looks kind of like this on your email. So there's a thing that says to please use the excuser link to notify me of any absences during the semester. So I'm asking everybody that is not going to be able to log in during the live lecture and that won't be able to participate in the quick check problems to just go to this link and just let me know on any given day if for some reason you can't make it for a couple of days or just one day. All you have to do is click on that link, and that's going to take you to a browser where you'll enter information. So first of all, it'll just be your name, your ID, when you're going to be absent or when you were absent if something came up. I prefer that you fill this out and send it before any expected absence. And then the very last box is just write a quick description of why you can't make it to class or why you can't log into class that day. So I know that this is a completely online class, but even then, usually at least 2/3 of the people, if not more, do log in during the live session. But if for some reason you've already known all semester that you're not going to make it to any of the live sessions, just write it in here for me. Say, hey, you know what? For whatever reason, I'm only going to be able to look at the YouTube videos. That's going to be fine, but you have to fill this out. If you don't, then I'm going to deduct participation points for any dates that are not covered in here. And you can go in here and log into this as often as you'd like. So this is going to be open all semester. So let's say 2 weeks from now you can't make it, fill it out. If it's 2 months from now, just let me know. This is just my way of keeping tabs on, people's ability to be in class. And so there's no extra assignment or anything like that. Just come in here, fill this out every time you can't make it. And that'll just help me out at the end of the semester, okay? So once you fill this out, I get a kind of a log of, everybody's entries, and it'll help me sort of calculate grades at the end of the semester. So if there's any questions, let me know. But I sent it in the announcement. It's also on Blackboard. I'll organize Blackboard a little bit better so you can have all the links I've been sharing with you in one simple to reach place as well. Okay.
Question, should we fill it out for previously missed classes or is this moving forward?
I'm not requiring anybody to fill it out for previously missed classes, but if you do have previously missed classes and it would help me out if you didn't notify me before, or even if you did notify me, it'll make my work a lot easier. So I won't have to search through my old messages. But yeah, so it's kind of on your good faith. I mean, if you don't mind taking a few minutes to just give me that information again, then I'd appreciate it. So
Okay, thank you.
yeah, not required, but highly encouraged. Thank you. Okay, so that's all I wanted to say about that for now. So we're going to go ahead and continue with today's lecture. Hopefully we'll be finished with chapter 2 today. And so just as a little bit of review, um, last time, so what I'm going to do right now is I'm going to write down some of the kinematics equations that we'll be developing some more today, but um, last time we developed the first of the kinematic equations, and and I'll just put here in parentheses for constant acceleration, which we'll never have cases where acceleration is changing for a particular step, but we have one that says that the final velocity is given by the initial velocity plus acceleration times delta time. Now, last time where we left off is we said that anytime we have a velocity versus time graph, as I've drawn here, there's a few features that we've discussed already before. One of them in one of these velocity versus time graphs, in some velocity time graph, we know that the slope is going to give you the acceleration. So this slope here. The other thing that we've discussed in the past is that the area under a curve is going to give displacement. And so this is our displacement. If we're looking at the x direction, this is the delta x bit. So when you look at one of these graphs, especially when we're dealing with displacement, well, usually we're concerned with a specific region of the plot from some initial time to some final time. And at each initial time and final time, there's going to be velocity coordinates, right? At an initial time, there will be initial velocity. At the final time, there will be a final velocity. And so from a graph like this, to obtain acceleration, what you do is you say, well, acceleration is going to be delta v over delta t. So in this case, using the labels I've put on that graph, you would take final velocity minus initial velocity, final time minus initial time. Now, the other part is, and what we're focusing on now is to find displacement. And we said, we call this delta x. So in this case, since it's the area, in this particular case, like I said, delta x is equal to the area in the interval we're interested in. So the interval from initial to final time. So here we'd be looking at this entire interval. And if we can find the area of this region that I'm kind of shading in, we can get the displacement. And so for this particular example, we have two areas. And it's a easy example because it's a nice straight slope. Doesn't matter what the shape of your curve is. You can, in principle, do it with any shape, but it's easier when we've got nice areas. So in this case, we got the area number 1. So delta x, which is equal to the area, in this case is going to be area 1 plus area 2 in that graph. In this case, area 1 is just, length times width. In this case, it's going to be, so we can say the width here is this delta t part. And then the length or the height is going to be from the bottom. So since it's for the rectangle, we're looking at basically from 0 to v initial. So in this case, you would say that the area would be V initial times delta t. That would give you the rectangular area. And then to get the area of the triangle, um, so for a triangle, it's always going to be 1/2 base times height. In this case, it would be 1/2 the base, this bottom part of the triangle. Let me just do it in a different color for just to highlight it. So we're looking at this particular bit right now. Well, the base is going to be delta t. And then the height that we're concerned with for this triangle is this amount right here, this height. And that height is going to be given by the difference between the final and the initial velocity. So you can stick that down there. So 1/2 base times height. Like I said, height is V final minus V initial. So, and that's what they're illustrating on the graph here on the right-hand side. And so they come up with an equation, and let's go ahead and derive it the same way they did. So it turns out, well, since we know delta x is area 1 plus area 2, then it's going to be V initial times delta t plus 1/2. And then you could leave this delta t times delta v, right? Because V final minus V initial is just delta v. Well, one thing that we can do to try to simplify this expression a little bit is, well, we can realize that there's this relationship up here that relates acceleration delta v and delta t. So in that process, we can go, we can do this intermediate step of saying, okay, well, if I solve for delta v from that equation that I've circled, well, it's delta v is equal to a times delta t, okay? So that means in this expression down here, we can substitute this expression for delta v for that delta v. So we're going to do a little substitution. And so that's going to give us that delta x is equal to v initial times delta t plus 1/2. And let's just kind of substitute it in. So delta time, and then here the delta v now becomes a times delta t. All right. So we're getting closer to the expression they have on the slide. Now we have these two delta t's that we have to combine. That's going to give us a delta t squared. So that's this part. And then we still have to include our 1/2, and then the acceleration goes in there. And then everything that's up at the front, we don't forget about it. And there it is. And that says delta, the displacement is equal to this expression. You can rewrite it in terms of finding x final, because we know that delta x is equal to the final minus the initial position. So you can rewrite that expression as x final minus x initial equals v initial times delta t plus 1/2 a delta t squared. And then to find, once again, like, so all I did here was I replaced the delta x for x final minus x initial. And so the final step, if you want to have it look like what's on the screen here on the slide, you just move the x initial to the other side. So you have final is equal to the initial position plus v initial delta t plus 1/2 a times delta t squared. So took a little while, but this second equation is what we will call the second kinematic equation, okay? So, and I'll try to copy these equations to the next screen a little bit later, but so we have this equation, x final is equal to x initial plus v initial delta t plus 1/2 a delta t squared. So what we're doing right now is we are developing basically a toolbox, a set of tools to help us solve problems. So, and it turns out that there's going to be one more equation that we'll come up with. And that equation we can obtain by combining equation 1 and 2. So we combine equation 1, 2. So there's some algebra steps. You get a third equation. The thing that's nice about this equation is that it's an equation that involves velocities. It involves everything except time. So here the equation says that the final velocity squared is going to be given by the initial velocity squared plus 2a times delta x. And so I'm not going to go into the details of deriving that from the first two equations. If you're really interested, you could do the algebra and check for yourself. But for this class, we're mainly these are gonna be the sort of the basic kinematic equations we'll use. These are the ones you guys have to memorize, or at a minimum, kind of have it in your set of notes that you have quick access to. And we'll be using these equations for most of the semester. And we'll be doing some calculations or solving some problems in a little bit. So just to go over some of the details of these equations, just to make sure everybody understands. Now, one thing that you'll notice is on the slides, they usually have, for example, for final velocity, they'll put a little X, letting you know that we're looking at it in the X direction. The way I've written them is sort of a general expression. We can put an X if we're looking at X, or if we're looking at vertical motion, we could put in parentheses and put a little Y there. But hopefully it's clear that, so all these symbols represent values, right? So for the first one, it says the final velocity is equal to the initial velocity plus acceleration times delta t, which is a time interval we're interested in. For the position, similar situation, we know x final, x initial, initial velocity, time, acceleration. And the whole point is that the next exercises are going to teach us how to use these equations. Basically, it's going to be a matter of setting up a problem, making a list of what we know and what we don't know, and hopefully we can identify an equation where where we know all of the parameters except for one, which is the one we're looking for. So in all of this, one of the things that you might notice is this is the first time we have equations that have a square term in them. Right? Equation 2 has this t squared term. The velocities have this squared term on the velocities. And so the next few slides are geared at sort of getting a more intuitive sense of how these equations work. So let me just copy these kinematic equations real quick so I can put them on the next slide. Let's stick these guys over here. I can figure out how to move it. Anyway. Come on, kinematics equations. I believe in you. Oh, it's only part of them. Okay. That's good enough. So when we're looking at quadratic equations, the idea is that you have this, so you can say in this case, for example, for the expression y equals to ax squared, in an equation like that, what you would say is that in this relationship, y is proportional to the square of x, meaning that if you double x, you're gonna increase y by a factor of 4. So, and you can see the example, there's a graph there that kind of shows what the curve would look like. So in that case, it has this kind of curve shape. This would be a equals x squared. And so in this case, if we say, okay, well, what happens when x is equal to 1? Well, in that case, y would be equal to a times 1, which is just a. And so at x equals 1, right here, you could say, okay, well, this point is equal to a. when you say x equal to 2, well, 2 times 2 is 4. So then y would be equal to 4a. So by the time you get here, this thing has increased amount about right there. So that's going to be 4a. You can imagine how this continues, right? If you go to x equal 3, then 3 squared is 9. So you have a value of 9a. So by the time you get to here, this point up there is, you know, it's not to scale, but up here you'd get something like 9a. And that kind of determines the shape of the curve you're going to get. One nice thing is that you do have this ability to develop ratios. So for example, let's say that somebody gives you, maybe they give you information on a set of points that we can call, maybe they give you the values of, so let me draw this again real quick. So let's say that you're going to solve a problem. And there's these 2 points of interest. One of them here is x1, where it has a matching coordinate y1. And the second coordinate is x2, that has a matching coordinate y2. And let's say that we are given, so let's say that we know values x1, y1, and x2. Well, you can use the quadratic relationship and or to basically, you can use it to calculate the unknown, which would be y2, for example. But one nice thing that you can do is you can say, okay, well, in the case of y1, we have y1 is equal to a times x1 squared. The a is the, you know, it's a constant. And in your equations, you'll find that there's going to be some quantities that will be constant. And then for y2, well, you're going to have y2 is equal to a times x2 squared. Well, you can set up a ratio between these that where you can say, well, y2 over y1, if you just plug in the values, you're going to get that equals a times x2 squared over a times x1 squared. And then you notice that the a's cancel out so that you have y2 over y1 is equal to x2 squared over x1 squared. So something like this would be useful if you wanted to calculate y2, then you just have to get rid of the y, put it on the other side, and you get your answer. Another thing that pops out of this relationship is you can factor out the square, so you get y2 over y1 is equal to x2 over x1, and that quantity gets squared. So it's a nice way of understanding how a problem is going to scale according to the square law. So if you have a ratio here of x's that is a ratio of, like, let's say 3 to 1, where x2 is equal to 3 and x1 is equal to 1, then you know that y2 over y1 is going to increase to a value of 9. So in other words, so from this, as a little bit of an example, let's say x2 is equal to 3, let's say x1 is equal to 1. This ratio, 3 to 1 squared, gives you 9. So you know that the ratio y2 over y1 is going to be also equal to 9. So it's telling you by how much it's going to increase. So if nobody told you what y2 equaled, but you knew all the other ones, well, even if you knew x2 and x1, and you know that it's equal to 9 times higher, then you know that there's going to be this increase by a factor of 9. So that y2 is going to be equal to 9 times whatever y1 was equal to, okay? And so it just, if you've never played around with equations like this, it's not a bad idea to just really understand how they relate when you have a quadratic relationship. And everything that I just said is kind of covered in that slide. So let's go ahead and do a real life problem here. So I'm going to copy our kinematic equations once more, or try to anyways. All right. So for this problem, it says here, so we're going to analyze this problem of coming to a stop in a car. It says here, As you drive in your car at 15 meters per second, which is just under 35 miles an hour, you see a child's ball roll into the street ahead of you. You hit the brakes and stop as quickly as you can. In this case, you come to rest in 1.5 seconds. They want to know how far does your car travel as you brake to a stop. So this kind of a problem is useful, for yourself in case you ever um, you encounter that. I mean, it could be a child, it could be a puppy or something. But the idea is you're driving. And so notice what I'm doing. The first thing what we do is we make a picture of the problem. So here's our car. And so they tell us that we're moving at 15 meters per second. So that's technically, that's going to be our initial velocity. We're going to say V initial is equal to 15 meters per second. And then it says you see a child's ball roll into the street. You hit the brakes and stop as quickly as you can. So you're driving at 15 and then you're going to hit the brakes. And so from this moment to when you stop, so notice it says you're going to stop as quickly as you can. So at some point later on, your car will be here. And so our final velocity, since we're stopped, we know we're going to be at 0 meters per second. And so this entire time we are applying brakes. And it also says that you come to rest in 1.5 seconds. So from that starting point to that ending point, it took you a delta t equal to 1.5 seconds, all right? So there's that information. And now we want to know how far did you travel during this time from the moment you slammed on the brakes to when you actually stopped. We want to know what is delta x. That's the whole point of this problem. So, all right, let's say we write down the things we know, what we don't know. So we know initial velocity was 15. We know the final velocity is going to be 0. We know delta time is equal to 1.5 seconds. What do we not know yet? Well, they didn't tell us explicitly what acceleration is. And the delta x is what we're trying to figure out, right? We want to find out what's that distance you covered. So right off the bat, looking at the equations, well, these equations, if you want to look at the one that gives you the delta x, so in this case, all of the ones that have delta x also have acceleration. So there might be an intermediate step. So maybe before getting the answer, which is for delta x, what do we need to do? Well, we need to find acceleration. And so this equation 1 is basically the equation for acceleration that we talked about before. Acceleration is delta v over delta t, right? So these two are really closely related. So we're going to use that to first find acceleration. Once we have acceleration, then we'll be able to plug that along with all the other stuff that we were given to figure out the distance, all right? So in this case, for the acceleration, we're going to say, well, it's final velocity minus initial velocity over the time interval. We already know the final velocity is 0. So in this case, we'll plug in our 0 minus initial velocity of 15 meters per second over the time of 1.5 seconds. So basically, we have this expression that says negative 15 over 1.5. And this is going to give us an answer in meters per second squared. So what happens when you do 15 divided by 1.5? What's the answer there? So it should be, yeah, so it should be negative 10 meters per second squared. So one thing to notice right away is we got this negative value. This negative 10 tells us that the acceleration is the opposite direction from the velocity that we started off with, from the initial velocity. So in this problem, since we were moving to the right, then that means the acceleration is in the opposite direction, and it has a value of negative 10 meters per second. So it's telling you it's working against velocity. If it had been positive 10 meters per second, then instead of slowing down, you would be speeding up and you'd never stop. Okay, so we've got this value, we've got the acceleration. So which equation do you think we can use now to get the distance? So let's take a look. First of all, first equation doesn't have any delta x, so that's not going to take us anywhere. Next equation includes the x final, x initial. And just to help you guys out, I mean, we could look at it this way also. If you want to keep it in terms of xf and x initial, well, in this problem, we could set it up so that where we start off, we can define that as our 0. In this case, positive x is to the right. And so the place where we finish our motion, that's our x final. So if x initial is equal to 0 and x final is what we're looking for, then delta x is actually, because of this expression, well, we know delta x in this case is exactly equal to just x final. So when you look at equation 2, well, that one's kind of nice because we're looking for x final, x initial is 0, velocity initial we already know time, we just calculate acceleration, and once again we have time. So that's one possible equation we can use. You could in principle use a third one as well. It also has, we already know everything except for delta x, so that would also be an okay equation to use. So really it's a matter of which one might we think is the easiest one to use. So just for simplicity, let's say we use, so we can use either 2 or 3 work. Let's go ahead and use equation 3. If we use equation 3, I'm going to write it down. Velocity final squared in the x direction is equal to initial velocity squared in the x direction plus 2 acceleration in the x times delta x. So really the point here is we're eventually going to want to find delta x. But it turns out we can get rid of a few things, right? We know that final velocity is equal to 0. So that means this term on the right-hand side is going to be, basically gets canceled out. So this part goes to 0. And so that's going to make the calculation a little bit more, well, straightforward. So now if we rearrange, we're going to get minus v initial squared, the x, equals 2a times delta x. And then finally, to solve for delta x, we get delta x is equal to minus v initial squared over 2 times acceleration. So this expression is going to give us that distance. And so now all we have to do is plug in the values. So if we stick in a minus and then initial velocity was 15. So we put 15 meters per second squared. Divided by 2a, well, it's going to be 2 times a, we had found it earlier, was negative 10. So that's going to go in there. It's minus 10 meters per second squared. So then you can plug that into your calculator, get an answer out. And so in this problem, they use, well, actually, it's actually nice that we use the equation 3 because in the slides they use equation 2, and hopefully we should get the same answer. But for this problem, let's let me go ahead and just copy this thing to, well, I have space here, not too much. So just carry it over here. So we have this expression. So what do we get when we do 15 squared? Is that 1? Can't do math this morning. 69, somebody? Come on, guys, help me out.
225.
Thank you. All right, so we got 225. So keep in mind so it's important to, until you, until you get used to it, you really should write out all your units. So it's going to be negative 225. And even that squared applies to the units. You're going to have meters squared per second squared over 2 times negative 10 is negative 20 meters per second squared. In this case, the negatives cancel out, and then you've got 225 divided by 20, right? So we go here and we say divided by 20. That's going to give us 11.25. On the slides, you notice they write down 11, so that's how it ends up running out to down to 11. And then for the units, this second squared cancels with this second squared, and then you've got meters squared over meters, so you get an answer in meters. So this is always a really good way of checking that you did it right by keeping the units in there. So in this case, we get that our delta x is equal to 11 meters. And the fact that it's positive means that it's to the right. So it's 11 meters to the right. But the positive kind of handles it. If it had been negative, it'd be the other direction. Okay. So, and so in this case, 11 meters, it's, 30 something feet, which hopefully is about right. And I usually tell people if you are new to driving, one day when you're on a road that's where there's no traffic, if you've never slammed on your brakes, I encourage you to do it at least once, every once in a while, just to understand the limits of your car, right? I mean, if you've never done that and you don't know what your car can do, then it's a good idea to just see what happens, right? If you slam on the brakes going 35 miles an hour, hopefully you stop really soon. But you don't want to find out what your car can do when you actually need to use it, right? When you actually have an emergency in front of you, if it's like a child or something, or maybe it's a car that's just like stopped or going really slow. You want to be able to be, have that safety of knowing, well, yeah, if I stopped, I can actually do it in this much space. Oftentimes, and what later on in the semester, we'll get into this subject a bit more, and we'll talk about why you have to be more careful when it's rainy out, or if you're like on a dirt road versus pavement. The quality of roads determines also how quickly you can brake. But in a problem like this, now right? It's so you're like, okay, well, 35 feet, you can hopefully have a sense of how far that is, and in some cases you'll realize that you need more space to stop. I mean, instead of going 35 miles an hour, maybe you were going 50 miles an hour, and so all of a sudden at 50 miles an hour, your distance is a lot different. So that's why it's really important that you don't speed when it's low speed limits, because one of the things that you learn, and let's actually analyze this a bit more real quick. So if you got delta x and your equation is v initial squared over 2a. For this particular car, we know that the acceleration was 10 meters per second squared, but you can kind of see how if you had a higher velocity here, the delta x, it's not going to be a linear relationship. And so you're going to probably stop in it's going to take you a much longer distance to stop if you're going a lot faster. So I'm going to skip this problem, but this one's talking about Spud Webb. And the only reason I bring it up is he used to play in the NBA, not anymore. Some of you may remember him. Some of you may have just heard of him. But this guy was amazing. He was 5'7". He could jump over a meter off the ground. And if you do internet searches, I think there's even some footage of him dunking the ball, which is pretty awesome. If I find a link, I'll show it to you guys next time. But so for all of you people that are short and like basketball, I mean, in principle, you can eventually jump pretty high if you really want to. Moving along. So now there's another problem I'd like to do. We're going to go ahead and keep going to the next section here, solving one-dimensional problems. Mainly because I do want to emphasize that there is kind of a method to solving these problems. Everything from being able to understand the word problem effectively, to setting it up, and to figuring out, well, what's the first step? What's the second step? And then once you get the answer, well, how do I know that I did it right? And, is it reasonable? And so these next few slides talk a little bit about that. So anytime you see a problem, you're going to be looking for keywords to determine, well, what kind of a problem are we dealing with? And so if you see, for example, that it says that there's a bicyclist riding at a constant 7 meters per second, well, you know that this is a problem of uniform motion with constant velocity. Constant velocity means acceleration 0. And so that automatically means that your equations become more simplified. If you look at what I mean by that is, so for example, if we look at the kinematic equations that I have here on the top right, um, if you've got uniform motion where acceleration is 0, well, look at how much simpler these equations get. Equation number 1, and let me just write it here. Let's say if acceleration equals 0. In this case, equation 1 just becomes, well, final is equal to initial velocity. Equation 2 becomes, you get rid of that very last part, so the final is just equal to the initial position plus v initial times delta t. And if acceleration 0, then equation 3 becomes v final squared is equal to v initial squared. And that's it. Everything else is 0. So the kinematic equations that I wrote here at the top, they're more general. They apply to all cases, either when acceleration 0 or a constant. But that's part of what this is about, is you first read the problem and try to decide, what kind of a problem you're dealing with. The next part is to really look at what they're asking you in the problem. So are they looking for a graph? Do they need a number? Do they need an equation? That's also going to guide how you approach the problem. And so once you determine, okay, well, what kind of a problem is this? Jumping into it, the first step in solving a problem like this, or any problem, is you always want to draw a picture. And you've noticed, hopefully, that in almost every problem we've done in class so far, I always draw a picture of the problem. And that helps you visualize what they're talking about. A lot of times in your homework or in tests, you're not always going to have a cartoon of what's going on. Most of the time, you will have just a word problem, and it'll be your job to actually draw a picture of it to help you visualize it. And that's a critical step. That's when it helps lay out everything about the problem, and it helps you chop it up into smaller pieces, as you'll see is necessary sometimes. So, and then I'm going through these quickly because there's a little list coming up that summarizes everything. But the final step after you go through and you pick your equations and you get the numbers, you always want to stop for a minute and check and see, okay, well, do I even have the right units? Does this number make sense? I mean, is it going to make sense that, for example, a mosquito can fly at like the speed of sound? That's unreasonable. Or does it make sense that, that it took like 5 kilometers to stop my car when I push the brakes? If you get a huge number, you're like way off, very likely. And this book does a good job at giving you word problems where the numbers they choose actually reflect reality kind of closely. So they're not just picking random numbers. They've thought about the kinds of parameters that would give you a reasonable answer. So yeah, this is the part I wanted to get to. So in essence, these are the steps that I usually like to highlight for people. So steps in solving problems. Now, for this chapter, they say these are the steps for solving one-dimensional motion problems, but you'll see we'll write these steps over and over throughout the semester, and even for other topics, it's going to be a very similar situation where the first thing that you're going to do is you're going to draw a sketch. And I find that when people don't draw a sketch, a lot of times people get the wrong answer because they just visualized it incorrectly. If I ever give you a problem and you don't draw a sketch and you give me the wrong answer, well, there's no way to really give any partial credit because I can't tell what you were thinking or how you thought the problem was set up. But if you have a sketch and I see there's something obviously wrong, well, then I know, okay, you got stuck in the initial part, um, and then I can be a little more lenient with giving credit for this is especially important like for things like tests where I'm manually grading things. The next part after you draw a sketch is you want to determine or establish a coordinate system. So you've noticed that whenever I draw my pictures, a lot of times I'll tell you what direction is positive X or what direction is east. So that's also critical to make sure we get our signs and directions correct. The next part is we're going to define some symbols. So for example, when they tell you we're moving at a speed of 15 meters per second, well, right away we say things like oh, final speed or final velocity, for example. That's the actual property. And we might say, well, we're going to define that as v final, maybe. And if it's in the x, we'll put an x there. So that's what it means by defined symbols. They give you acceleration, then you say a equals whatever it is. And you do want to do that with each piece of information. The next part is what I say, where we list whatever is known and all the unknowns. And literally make a list of this. It does help to just have everything front and center. A lot of times when I draw a sketch, I'll put all the, I'll put one velocity on one side of the cartoon, another one at the other side of the cartoon. But even after you do that, it's good to just have a list all together in one place. That way it helps you figure out what's the best equation to use for this problem. And so the final thing is going to be, in some cases, you might go from a sketch to drawing a motion diagram. You might go from drawing a sketch to making a little graph that shows the information, whatever it is to kind of help with your process of solving the problem. So let's kind of do one of these problems together. So here in this case, this problem is about the kinematics of a rocket launch. So it says here, a Saturn V rocket is launched straight up with a constant acceleration of 18 meters per second squared. After 150 seconds, how fast is the rocket moving and how far has it traveled? So for this problem, this is example 211. So it's going to be launched, presumably from the flat ground. You get this little rocket. And so it's going to have a constant acceleration of 18 meters per second squared. We want to know that after a while, some properties of it. So I'll go ahead and draw the little rocket up here. So one thing that they don't tell you is they don't tell you it starts from rest at 0, but because it's a launch, we know when things get launched, usually they start off at 0 meters per second, or from rest. So we can right away also add v initial. Since this is a vertical motion problem, we can say v initial in the y. So what I'm doing so far here is the coordinates I've established are that, this right here is my positive y direction. In this case, there is no x component, but if there was, it would be to the right. And so then it says after 150 seconds, we would know how fast it's going. So after 150 seconds, we know we travel a certain distance, some kind of delta y. There's also a delta t that it took to get to that height. And we also know that up at the top, there's going to be some final velocity in the y. So the moment we stop the clock at 150 seconds, we can check things like final velocity. but that hasn't been given it to us yet. What has been given to us is the time, right? So they tell us the delta t is 150 seconds. And so for this problem, what we want to know is how fast is the rocket moving and how far has it traveled? So after we've done our sketch, we've made our coordinate system, we've kind of defined some of our symbols. I mean, I didn't write specifically, I just kind of said it as I solved it, but if it helps you out, you can say final velocity equals v final in the y, something like that. But anyway, let's make a little list here. So we have v initial is 0. V final, we don't know. That's one thing we're trying to find. And even better, I usually try to put the things I don't know in a separate little column. So maybe here we could say V final in the Y, we don't know. So I meant this to be a question mark. We have delta T, which we do know, and that's 150 seconds. Delta Y, the displacement, we don't know that either. And the other thing we do know is the acceleration. It's a constant acceleration of 18 meters per second squared. So there's the things we know, things we don't know. So we start off with the first part that's asking, so part A is really asking about how fast is it moving at that point. So V final in the Y is what we're looking for. So is there an equation that we can use to help us solve this problem? And let me see if I have a nice clean copy of these. So I'll copy them down here again. So here's our kinematic equations. And it looks all jumbled there. I'll just stick them down here. Hopefully you guys can see them down there. Anyway, sorry for the ugliness there. So let me just write it once more up here just to make it clear. So we want to find out what is that final velocity in the Y. That's our goal. So from those three equations here at the bottom left, which one could help us find the velocity? Any guesses?
1.
Yeah, so if you look at equation 1, V final in the Y equals V initial in the Y plus A delta T. Well, the nice thing about this is we know initial velocity is equal to 0, so that's going to make it simple. So to get the final velocity, it's just going to be A times delta T, which will be 18 meters per second squared times the time of 150 seconds for this problem. And so once you do that, I think they did it maybe in the next step here. Here's the expression where basically they took 18 meters per second multiplied, or meters per second squared times 150. That gives you 2,700 meters per second. So this is the answer for how fast the rocket's going after a little bit over 2 minutes, so 2.5 minutes. Okay. Does anybody by any chance know what the speed of sound is? So I don't expect you to, but speed of sound is usually around 340 meters per second. So this gives you an idea of how many times faster than the speed of sound that rocket's going after 2.5 minutes. It's going pretty freaking fast, right? I mean, you're talking about 7 or 8 times the speed of sound, which is actually something a rocket can do. These rockets, no, they're meant to go into space, so you have to escape the Earth's gravitational pull. So now that we've got the velocity, the second part of this problem was to figure out how far it's gone, right? So now we have final velocity. Well, is it going to be easier now to figure out the displacement? Well, in this case, if you, for example, so for equation 1, we can't use equation 1. There's no displacement term. Equation 2 does have a displacement term. And it doesn't even require us to know the final velocity. So we could use equation 2 in that case. And so for that case, I'll draw, let me use a different color. So let's just go in this little blank spot. So this is part 2 of the rocket problem. So we need to find delta x, or sorry, delta y, which is y final minus y initial. If we start off with y initial, and this is another thing we didn't write down, but y initial we can say is just 0 meters, right? If we start off at the bottom here. So basically, we need to find this y final business. And if we use equation number 2, so we're just going to substitute the x's for y's because we're looking at the vertical direction. In that case, it's going to be y final is equal to, you'd have y initial, but that's going to be equal to 0, so that just goes away, plus v initial in the y times delta t plus 1/2 a delta t squared. So we already said, we're starting at y equals 0, so that goes away. We're also starting from rest, so v initial in the y, we had already said here that's equal to 0. So this whole term also goes away. And so we're left with an expression that says y final is equal to 1/2 times the acceleration times delta t squared. And we can just plug those values in and get 1/2 times, we said acceleration, grab it from here, is 18 meters per second squared times delta t squared. So we'll put the square of this delta t, which is 150 seconds, in there. And so if you look at the right-hand side here, where they solved it, they essentially have that 1/2 times 18 times 150 squared. Don't forget to square it, it's very important. And you end up getting a number like 2 times 10 to the 5th meters. And if you convert that to kilometers, since there's 1,000 meters in a kilometer, that's the same thing as 200 kilometers. So this thing's gone way up into the sky. Does anybody know how high an airplane usually flies? Like when you just travel across the United States? Anybody? It's usually the part nobody pays attention to because you're just there trying to turn off your phone or get your movie set up, right? But usually they'll, a lot of times they tell you the altitude. And so, for example, planes, usually they're at about 35,000 feet altitude. So 1 mile is about, it was exactly 5,280 feet. So basically you're flying about 7 miles up in the sky. Now 1 mile is about 1.6 kilometers. So 7 miles in kilometers is going to be something around, what is that, like 12 or 14 or something like that. So something between 10 and 12 kilometers up in the sky. When you look at the height of this rocket, keep in mind in only 2.5 minutes, it went to roughly 20 times higher altitude than what an airplane does. Just to give you an idea of the kinds of scales and numbers we're talking about. So you probably couldn't see it. You definitely couldn't see it with your eyes after that time if you just looked up into the sky. All right, so this is a bit of a summary of the method used to solve these problems. I'd like to do another example. So in this case, we're gonna calculate the minimum length of a runway. And we're gonna, so right away, I always recommend you have your kinematic equations written down somewhere. And the quicker you can memorize them, the better off you'll be. That's the first one. Second one, And you'll see me write it in terms of delta x or just x final and x initial, but I mean, it's easier and faster for me to write it like this. So that's the second one. Third equation is v final squared is equal to v initial squared plus 2a delta x, okay? So let's look at this problem. It says here, a fully loaded Boeing 747 with all engines at full thrust accelerates at 2.6 meters per second squared. Its minimum takeoff speed is 70 meters per second. How much time will the plane take to reach its takeoff speed? So let's go ahead and draw the problem out. We know in this case, there's two things that we're gonna have to find. The first is gonna be the time. So our delta t is one thing we don't know. And then the second part is gonna be what's the minimum length of runway that the plane needs for takeoff. So minimum length, that means we need to find some kind of a distance, right? Some displacement. And after that displacement is when the airplane takes off. And so this is important because if you've ever driven by the airport here in El Paso, you know that sometimes when planes take off, they might take off pointing towards the city, right? I mean, they'll be pointing west. And a lot of times when you see planes take off, especially if you've ever been to like Bassett Place, you see those planes look like they're just almost grinding over the houses, just like right over them. And so if you do a miscalculation, if you don't press on the thrust hard enough, then that plane won't take off in the right distance. So all right, let's say we've got our runway. So right away, we can define this as our positive x-axis. We'll put a 0 down here. And then it says that the acceleration is going to be 2.6 meters per second squared. They want to know, so it says the minimum takeoff speed is 70 meters per second. So that means if it's going below 70 meters per second, it just can't fly. It's not going fast enough. So it needs to go at least that fast. So that means, so we're going to assume that you're here on the runway, you're waiting for your turn to take off. And so that's going to be the position. We're going to start off at x equals 0. Our initial velocity is going to be 0. After a while, this plane is going to speed up. And once it gets to the right speed, it's going to be able to start taking off. So at this point, the final velocity we set that we're dealing with is 70 meters per second. So we want to find the times that it's going to take for it to get from 0 to 70 meters per second, okay? So that's our goal, is find time to go from 0 to 70 meters per second, right? So what else do we know? So let's go ahead and write our list of things we know. V initial, 0. V final, 70. Acceleration, 2.6. And I think that's how we know, right? We don't know the time yet. We don't know the distance yet. So using that information, which equation can we use? Well, we see we've got both velocities and acceleration, and we want to find the time. Well, if we look at equation number 1, we can see that's got those 4 parameters, right? We got 3 that we know and the 1 that we're looking for. So let's go ahead and use number 1, and we're going to solve for time, or this delta t. So in this case, we're going to have v final minus v initial equals a times delta t. And then the next step, you just divide by a. So v final minus v initial over a. So plugging in the numbers that we know is going to give us the time. So delta t in this case is going to be the final velocity of 70 minus the initial velocity of 0 over an acceleration of 2.6 meters per second squared. So essentially, since this part here is 0, we're just doing 70 divided by 2.6. So if we do that here, 70 divided by 2.6, that's going to give us 26.9. So that's going to be 26.9. What are the units? Well, we're looking for time, so these things better cancel out to give us units of second. So 26.9 or roughly 27 seconds is how long it's going to take for it to get to that speed it needs so that it can fly up into the sky. All right. Next question is, what's the minimum length of runway that it needs? So basically, now that we know that distance, the time, we need to find the delta x at which it takes off. And takes off meaning it's going to fly up into the sky. So once again, we look at our equations. Well, the bottom two have a delta x term in them. We have, I guess in this case, we also can use either equation, right? So if you didn't have the time, you could use equation 3, where you would have to just rearrange to solve for delta x. In this case, because we just found the time, we can also use equation 2 and just plug in the values there. So let's go ahead and use equation 2. If you use equation 2, I'll just write it out for you one more time here. Delta x is v initial delta time plus 1/2 a delta t squared. The nice thing about this one is we start off at initial velocity of 0. So this whole thing goes away, equals 0. So we have delta x is equal to 1/2 a delta t squared. And we're just going to plug our values in now. We have 1/2. Acceleration was given to us. It's 2.6 meters per second squared. So remember, this acceleration is a constant. It's just a measure of how hard they're pushing on the gas pedal, right? Or, you know, how far they move the little lever to get the plane to move. And they just leave it there until it speeds up to the right speed. And then we add the last term, the delta t squared. So we found a delta t of 27 seconds. So we're going to take that and square the whole quantity. So if you do that, you know, you type it in your calculator. We go to this page here. So you can see there's the expression for using equation 2. Everything cancels except for the last part that has the 1/2, the 2.6, and the 26.9 squared. So when you go through and calculate that, you get a value for delta x that's about 940 meters. So pretty close to 1 kilometer. And if you look at runways, you'll notice runways are usually about a mile long, more or less. And that's what determines whether certain airports can handle certain airplanes. If your airplane's too big and it needs a lot more space, then it probably can't land in a small airport with a short runway. Any questions? Okay.
Professor,
Yeah.
how did you cancel the VI change in T?
So that's so I kind of made a substitution here. So I know that my initial velocity, this part here, was equal to 0. We start off at 0. So when you plug that into that expression, it cancels out. It's 0 times delta time, so it's just 0.
Oh, okay. Thank you.
All right. So we have some time to set up a problem here. Let's see how far we can get. So in this case, they're talking about an African antelope that's known as a springbok. It says will occasionally jump straight up into the air, a movement known as a pronk. It says the speed when leaving the ground can be as high as 7 meters per second. So in this case, it says if a springbok leaves the ground at 7 meters per second, how much time will it take to reach the highest point? How long will it stay in the air? And then when it returns to Earth, how fast will it be moving? So there's a few pieces of information that we'd have to know for that problem. And one of the things that we'd have to know, so let's actually draw it out real quick. So the idea here is you've got this field with this little animal. That's my springbok. And it says it's going to leave the ground with an initial velocity of 7 meters per second. And that's kind of all they tell us, really. And then presumably it's going to jump up into the sky somewhere. And it looks like a cockroach almost. But in this case, they're asking about how much time it takes to get up there. And then how long it'll take to stay, it'll stay in the air. So in this case, it's like kind of a two-part problem, right? Where time to reach the highest point, well, that's going from here to some maximum height, well, that we can call delta y. So that's gonna have some associated time. So this is part A. But then part B asks about basically total time in air, which is different, right? Because in that case, we're not just looking at the way up all the way to this delta y. So that's going to be one delta time, but then on the way down, that's another delta time that we have to consider. And then the last question is, when it does reach the ground, it's moving downward. Right before it hits the ground, it has some downward velocity. And so they want to know, what is this velocity equal to? Well, there's a few things that we don't know about this problem. One of them has to do with what's making the springbok slow down as it's flying upward, and then what's making it speed back up once it reaches its maximum height and starts going back down to the ground. And in that case, it is going to be the acceleration due to gravity. And so the next section is going to talk about problems that deal with free fall. So the idea here with free fall, and this is going to be an important discussion to, so what's missing right now from solving this problem is we haven't talked about the acceleration, and in this case, it's the acceleration due to gravity. And so this section about free fall kind of introduces that. So it says here, if an object moves under the influence of gravity only and no other forces, we call that motion free fall. So basically, this is motion under influence of gravity only. This is what we call a free fall problem. The other thing that's important to realize is all objects, basically the mass does not matter. And we'll talk about mass a little bit more, have the same acceleration. So what does that mean? Well, that means that if you drop something like a bowling ball and a pencil, they're going to accelerate the same way down toward the ground. So if you let's say you stand on top of a tall building somewhere and you let them go at the same time, they're going to hit the ground at exactly the same time, because their motion is only under the influence of gravity. And even though they have different mass, they're going to accelerate the same way. So if they start off at 0 meters per second, they're going to hit the ground at the same speed and at the same time. Now, the only issue with this is, well, in reality, there is air resistance. And so sometimes that air resistance can slow things down. This is the only reason that people wear parachutes when they go skydiving, or if you need to eject from an airplane for whatever reason. If it wasn't for air resistance, if the air wasn't kind of there helping to push the parachute up, you would just fall, and according to these rules. So you could say air resistance does slow you down. For most problems though, I'll say here, for most problems, so unless we tell you otherwise, we're going to ignore air resistance. It's just going to make the problems a little bit more easy to solve. There will be one or two introduced later in the semester, but for the most time, when you've got things falling, you can just ignore that there's air and wind, and you can assume that if you drop a leaf or a feather, it's going to fall at the same time as if you dropped a big rock. The only reason that in reality that doesn't happen is because air resistance keeps the light objects kind of floating a little bit longer. And this is actually very relevant to like the COVID-19 pandemic. If you've ever wondered anything about like, well, what's up with the 6-foot rule? Why 6 feet? Why not 4 feet? Why not 10 feet? Well, it has to do with the path that most of the projectiles that come out of your mouth take. And most of the harmful particles kind of hit the ground after about 6 feet. In reality, it turns out that there are some tiny particles that are so small that the air resistance doesn't let them fall to the ground. They just kind of keep floating around. This is the reason why they have to turn on fans at stores when you go visit them, just to make sure you're kicking out all these little tiny droplets that don't want to fall to the ground. But we'll do more problems with that next time. And we're almost done with this chapter, so we'll finish it off at the beginning of class next time, and we'll move on to chapter 3. So that's all I've got for today, guys. So if there's any questions, ask now. If not, I'll see you next time. All right. So that's it, guys. You have a great day. Bye-bye.
I have a question. I'm sorry.
I knew it. I always this happens right before I hang up. What's up?
I am so sorry. I got a Microsoft Teams email saying that I was added to Microsoft Teams
Oh,
for your class.
thank you for that. So that's related to what I talked about at the very beginning of class this morning. Everybody got an email with a link for the excuser like tool. So basically, in Microsoft Teams, I made a little team with everybody in it, and you won't have to go in and out too often. It's just whenever I ask you. So for example, if you can't make it to class on any day, you're gonna just click on that link that's in the email, and that's gonna take you to that Teams team that I created. But I don't suspect we'll be using it for many things other than just things like surveys and stuff like that. Okay.
Okay, thank you.
You're welcome.
Good question for me too, Professor. I sent you an email this morning, and you sent the email saying I don't have to attend the live sessions anymore. Do you still want me to fill out that Google form, or do you just want me to ignore that since I have the email?
Well, if you don't mind just filling it out, just fill it out. But I've already kept track of it, so either way. No.
Perfect. I'll go ahead and fill it out. That's not a problem.
Cool. Thanks. Anything else? All right, then. Have a great day, guys. Bye-bye.